capacity. Okay? So if we divide the amount of oxygen that's actually bound to hemoglobin by the oxygen carrying capacity of hemoglobin, okay, that ratio is the percent saturation. So if we figure out, and I'm going to just use some simple numbers here, if we figure out that the maximum oxygen carrying capacity of blood, 10 milliliters of oxygen per deciliter or 100 milliliters of blood, okay, but that, if we were to do a measurement of how much oxygen is found in hemoglobin, it's only 5 milliliters of oxygen per 100 milliliters of blood. Then we can say that that person's hemoglobin is only 50% saturated. It's only carrying half as much oxygen as it has the capacity to do. This percent saturation is related to the affinity of hemoglobin to oxygen. Okay. The greater the affinity of hemoglobin for oxygen, the more oxygen that binds to it. And the affinity of hemoglobin is going to change based upon the dissolved oxygen content. Come back to that. Now, when oxygen does combine with hemoglobin, it can do so in such a way that up to 4 molecules combine because you have 4 heme groups. This hemoglobin molecule would be fully saturated, 100% saturated. Okay. Now, this is a very, very important curve. It seems like in my life, every major standardized test that I've taken has included this oxyhemoglobin dissociation curve. This curve plots the dissolved oxygen content using units of partial pressure with hemoglobin saturation. Okay. What this curve tells me is that the higher the partial pressure of dissolved oxygen, okay, the higher the hemoglobin saturation, percent saturation. And this relationship is not a linear relationship, in which case the curve would look like this. It's actually more of a sigmoid relationship. Okay? A sigmoid is kind of an S-shaped curve where it kind of looks like this. Okay? And it's got a steep portion here. Okay. So that the higher the partial pressure of dissolved oxygen, in other words, the higher the concentration of dissolved oxygen, the higher the affinity of hemoglobin is for oxygen. The more it grabs onto oxygen, the higher its percent saturation. Now, let's look here. As long as your PO2 is about 60 millimeters of mercury, hemoglobin saturation is fairly high. In fact, at 60 millimeters of mercury, hemoglobin is 90% saturated. But look what happens if your PO2, and we're talking about arterial blood, if your PO2 drops below 60 millimeters of mercury. We enter then onto the steep portion of the curve, where hemoglobin saturation drops rapidly. Okay? And that's because the affinity of hemoglobin for oxygen is markedly reduced and suddenly gives up oxygen more freely. And this is actually a good thing. In the area of the lungs, okay, where the PO2 in the pulmonary capillaries and the blood leaving the lungs is relatively high, I'd say close to 100 millimeters mercury, then most of that oxygen is tightly bound to hemoglobin. Hemoglobin saturation is high. Now, when that hemoglobin then is carried by the bloodstream away from the lungs to tissues, which are more hypoxic, where the environment has a lower concentration of dissolved oxygen, all of a sudden we're taking that hemoglobin and bringing it from an atmosphere where the oxygen content is high to an area where the oxygen content is low. For instance, at a partial pressure of oxygen of around 40, which is typical of tissues, hemoglobin is only 75% saturated. So that means that if it was carrying 4 molecules of oxygen at the level of the lungs, it's going to give up one of those oxygens. It's going to become 75% saturated. Okay? And you can figure that out based on this hemoglobin dissociation curve. So it's very important that you're able to reproduce this curve. Partial pressure of dissolved oxygen, okay, is going to correlate with hemoglobin saturation. And this is a good thing. Okay? If blood, okay, did not have any hemoglobin in it, okay, then oxygen from the alveolus would diffuse into the bloodstream until an equilibrium is achieved. But there would be fairly limited movement of oxygen compared to if we dumped hemoglobin, red blood cells, into that pulmonary capillary blood. Okay? Let's suppose that in the alveolus the PO2 is 100, and in this situation where there's no hemoglobin, that oxygen moves across the respiratory membrane into the pulmonary capillary blood. Well, there's a limited ability of that oxygen to diffuse. Okay? And so we have a relatively small oxygen content within that pulmonary capillary blood, but it would equate to a PO2 of 100. If I add hemoglobin at a PO2 of 100, hemoglobin is close to 100% saturated. So many of those oxygen molecules are going to do what? They're going to bind to hemoglobin. As that occurs, what happens to the partial pressure of oxygen within the plasma? It falls because it's leaving the plasma and attaching to hemoglobin. So that renews the gradient that pushes more oxygen across. Okay? So the presence of hemoglobin allows for more oxygen to cross over and be carried by the bloodstream. Again, plasma has a very limited ability to dissolve oxygen and to carry it. But if I add hemoglobin to the equation, okay, at a dissolved oxygen content of 100 millimeters mercury, then most of these hemoglobin molecules are going to bind 4 molecules of oxygen. Okay? So that not only increases the oxygen carrying capacity of blood, but it keeps this gradient going. So that as that blood crosses the alveolus, more and more oxygen then keeps on moving across the respiratory membrane. So it increases the oxygen carrying capacity of blood. Okay. So let's see what happens when oxygenated blood from the lungs. Let's see what's happening. Oh, this is movement in the lungs. Okay. And this is going to be, think of this as the respiratory membrane, this is the alveolus, this is plasma. In blood that's returning, we'll call it mixed venous blood that's returning from the tissues, the dissolved oxygen content is low as reflected by a low PO2, 40 millimeters mercury. We said that the PO2 within the alveolus is relatively high, so we have a gradient. Okay? So that gradient is going to allow oxygen to move from the alveolus into the plasma. And as that oxygen is becoming dissolved, because of the high partial pressure, hemoglobin starts to pick it up from the dissolved form and bind to it, okay, creating oxyhemoglobin. Okay? So oxygen becomes dissolved, and then it rapidly then combines with hemoglobin. And so we have a continuous gradient being formed as blood is moving along the respiratory membrane. It keeps oxygen moving from the alveolus into plasma, as long as blood keeps flowing. Now, let's calculate now how much oxygen is being loaded up within the lungs. Okay? The way we do that is first by calculating how much oxygen is carried by hemoglobin. If we know that a person has a hemoglobin concentration of 15 grams per deciliter, we can multiply that times 1.34 milliliters of oxygen per gram of hemoglobin to determine the maximum oxygen carrying capacity of that hemoglobin. If we have 15 grams, it's going to be 20.1 milliliters per deciliter of blood. Okay? Now, when I do blood gases, one of the values that the blood gas is going to report is the percent saturation. So let's say that blood has a percent saturation of 97.4%. I can multiply the percent saturation times the maximum oxygen carrying capacity of that blood to determine how much oxygen is being carried by that patient's hemoglobin. Okay? So if I multiply 97% times 20.1, I get about 19.6 milliliters of oxygen per 100 milliliters of blood. That's the amount of oxygen being carried by that person's hemoglobin. Now, if I divide this value by the maximal oxygen carrying capacity, of course I would get percent saturation. Okay, I'm just reworking the numbers. So this value, does it tell me the entire oxygen content of blood? No. It simply tells me how much oxygen is being carried by that patient's hemoglobin. Within the arterial blood, where the saturation is 97%. Okay?
So you would have to provide us with the percent saturation?
Yes.
Okay.
And I would do that by simply giving you blood gases,
Okay.
blood gas values. Another way percent saturation is expressed on blood gases is SaO2. That's how they express it on blood gases. Stands for arterial oxygen saturation. Now, to get the total oxygen content, I would have to include how much oxygen is dissolved in that arterial blood. Okay? At 37 degrees, which is body temperature, 1 milliliter of blood carries 0.00003 milliliters of oxygen per tar, per millimeters of mercury. Okay? So that if we're talking about 100 milliliters of blood or a deciliter, I'd have to multiply 100 times this figure here, and that would tell me that I can have up to 0.003 milliliters of oxygen per 100 milliliters of blood. In other words, carried in the dissolved form. Okay? That's per milliliter of mercury. And we know that in arterial blood, the partial pressure of oxygen is closer to 100. So if someone has a partial pressure of oxygen of 100, I would multiply that times the maximum amount of oxygen that can be dissolved in blood, and that would tell me that, okay, that blood is carrying 0.3 milliliters of oxygen per deciliter. Okay, so I can figure out the amount of oxygen that's physically dissolved and add that to the amount of oxygen that's being carried by hemoglobin to get the total oxygen content. So for calculating dissolved oxygen, I simply take this number, 0.03 milliliters of oxygen per 100 milliliters of blood. That's the amount of oxygen that can be dissolved in 100 milliliters of blood per millimeter mercury, in other words, per PO2, expressed in milliliters of mercury. And I actually multiply it times the actual partial pressure. Of course, the higher the partial pressure of oxygen, the more oxygen is dissolved. Does that make sense? Okay? So what happens when blood becomes loaded with oxygen in the lungs and that blood is carried to tissues? Okay? The first thing that happens is dissolved oxygen within the plasma, okay, which has a PO2 of around 100 milliliters of mercury, that leaves the capillary and enters into the interstitial fluid, where the PO2 is lower. It's around 40 milliliters of mercury within this interstitial fluid. So because there's a gradient, okay, the dissolved oxygen starts to cross from the bloodstream into the interstitial fluid of the tissue. Okay, then it's going to move from the interstitial fluid into the cell. Okay? Now, once we start to lose dissolved oxygen from the plasma, that PO2 is going to drop. Okay? In fact, what's going to happen is that as dissolved oxygen crosses the wall of the capillary into the surrounding tissue, okay, this number is going to start to fall toward 40. Now let's go back. As the PO2 drops from 100 to closer to 40, up here 40, we're going from 100 to 40, okay? What's happening to percent saturation? It's decreasing. Remember, percent saturation is a reflection of the affinity of hemoglobin for oxygen. So as the dissolved oxygen content falls, the affinity of hemoglobin for oxygen decreases. It starts to give up oxygen. So that's what happens within the tissue. So the dissolved oxygen content first falls, and as that happens, hemoglobin begins to desaturate. Okay? I think we said that at 40 millimeters, hemoglobin saturation is about 75%. So each hemoglobin molecule, theoretically, is going to give up one of its 4 oxygen molecules that's carrying. Does that make sense to everyone? These concepts are a little bit difficult, but if you review them, if you read the book and review, it'll make sense. And if you do those problems, the purpose of those problems is simply to make you more familiar with these contents, these concepts rather, and help you learn how to manipulate the numbers. So again, in the lungs where the PO2 is close to 100, hemoglobin is 100% saturated. In the tissues where the dissolved oxygen content falls, okay, the PO2 is close to 40 millimeters of mercury, hemoglobin is less saturated. It's only 75% saturated.